example, the sun provides light. So during the day, we can see different things because of the sun. So the sensors similarly can capture images of the day because they're using the energy from the sun. Active remote sensors are situations where a sensor emits its own energy and then records the backscatter. The backscatter is the rays that are reflected back. And this backscatter is important because different objects will reflect different characteristics, will reflect the rays based on the characteristic of that object. So an example of active remote sensor is LiDAR, light detection and ranging, or synthetic aperture radar. At some point, we will give more details about these. I just thought, because of the kind of audience that we have, it's possible that there are people who've never seen a remote sensing image. So, for example, this is an image that is captured by a passive sensor, Landsat. And it shows us the image that our eyes can see. So it's called a true color image, because if we looked at the Earth, this is how it will look like. Because of the tools that we have in remote sensing, we can have a false color, which basically means that we change the bands, we change the layers from remote sensing so that it shows us in detail the particular things that we are interested in. So for example, if we are interested in mapping the lake or mapping vegetation, then the vegetation will be in red because vegetation reflects near infrared. And then because water absorbs the near infrared bands, the water will be darker. So we can clearly see the distinction between water and the vegetation. And for example, when we carry out our analysis, this is how we, for example, we can detect the water. So that is a brief of how you move from a basic remote sensing image to how you extract, because indeed, extracting images and extracting objects and extracting information from remote sensing, that is a main purpose of remote sensing. That we can understand the objects, we can understand their characteristics. An example of an active remote sensing system is LiDAR. And LiDAR stands for light detection and ranging. What happens is you have a laser that can be on an aircraft or can be on the ground. This laser emits light rapidly. This light hits objects and then is reflected back. So what a laser system does is to calculate the distance between the emitting platform and the object. And from these, because the emitting object, we know the coordinates of the emitting object, and there's something called differential GPS. So it means it is locked. We know the coordinates, and if it moves, we understand how the object has moved. So from these, we can be able to calculate the coordinates of our objects. And when we have these different distances, then we can be able to produce a model of the object that we are interested in. And multiple returns and the densities of the emitted lights can support us even in mapping tree canopies and mapping 3D objects. As an example, this is an image that has been captured from LiDAR. So we can see different heights. So for example, we can see a 3D image of a stadium, of a building. And what I need to highlight is for each distance that LiDAR measures, it's called a point. So when you have many points, then they are called point clouds. Basic concepts of remote sensing. One thing that you'll always hear about remote sensing is the resolution. So what is a resolution? A resolution is basically a degree of fineness or detail with which information is captured. And this is important because it determines how we can use data from remote sensing. And in remote sensing, there are different types of resolution. There's spatial, temporal, spectral, radiometric resolution, and sometimes there's a thematic resolution. So we'll talk about spatial resolution. The images that we see are two examples of images in the same place. So one is low resolution because it captures low detail, and the other is high resolution because it captures high detail. Spatial resolution is basically a measure of the finest distinguishable detail in an image in terms of space. And I'm sure we know this because of the gadgets that we now have. You have phones that are a number of megapixels. Basically, it tells you about the detail that that phone can capture. Then there is temporal resolution. This is the detail in terms of time. Remote sensing data can be captured, for example, per day or once in a month. So when you're talking about the time space between one data and the next, then that is temporal resolution. Then the spectral resolution. We talked about the electromagnetic spectrum and about how different parts of the electromagnetic spectrum can be used for remote sensing. So the ability to define fine wavelengths. So for example, when we have the optical range of the electromagnetic spectrum, if we divide it into fine details, so for example, we can divide it into blue, green, and red. In some instances, we can go into the rainbow and divide it into 7 colors instead of 3. So those fine divisions are what we call spectral resolution. And because of the wide range of the electromagnetic spectrum, it means it's possible to divide it into as many as 200 ranges. And these ranges capture different things, so helping us to get information about objects in detail. Then there's radiometric resolution. This is basically how an image is stored. So for example, if you have a black and white image, it can only store black and white. Then it means that resolution is very low. It can only store black and white. But if you have one that can store in color, the resolution is higher. So you see beyond black and white, you see other colors. So radiometric resolution is just how much detail can be stored in a single pixel, in a single element of a remote sensing image. Then now let's look at, in brief, some of the remote sensing satellites. My intention here is not to go into the details of them, into the details of each of them. You will have the slides, and in each of the slides we have a reference so that you can go into the details. But for example, here we have different satellites: the spatial resolution, the temporal resolution, and the spectral resolution. And these are important because you choose a particular satellite data depending on the use that you have. Then here again, I have an example of sources of data because I know there are people who, after these, they will want to explore with different kinds of data. So these are some links where you can get some data. And again, I'm not going to talk into the details of them because you'll have these slides and you can check each of them. But I've highlighted two. One is the Google Earth Engine, because what happened when satellite imageries became free and open, Google archived every satellite imagery that was free and open, and also provided a scripting platform where you can access this data, you can analyze this data, you can visualize this data. So when you go to that link for Google Earth Engine, you'll be able to access the data and you can be able to interact with the data. Then there's also a free LiDAR data. So this is high resolution, and you can also play with it. You can also play with the data and learn from the data. At the end of this presentation, I'm going to show us a brief of the drone data that is freely available and that we can use. So then we go to the main reason why we carry out remote sensing. The main reason why we carry out remote sensing is so that we can analyze and so that we can understand objects on the surface of the Earth. So in terms of the steps of carrying out a satellite image analysis, for those who are getting confused, a satellite image, and when you talk about a satellite image and when you talk about remote sensing image, we're basically talking about the same thing, only that in this case we are talking about the fact that the image has come from satellites. So the first thing is that you define the objective. So for example, my objective can be to map. My objective can be to map the various land uses in a city. And then I collect data for that, for achieving that objective. And then I process the data. I process the data. Basically, I move from an image to objects that I can identify. And then I analyze the data. Analysis means what other contextual information can I get about the data? And then I carry out an accuracy assessment, right? So that to confirm whether the results that I'm getting, do they relate to the reality? And then I interpret these results. So these are the key steps. There are other mutations that you may get from literature, but these are the key steps that at any point we need to be carrying out. In order to carry out image analysis, there are two methods. We talked about an image, and we've talked about the smallest unit. And the smallest unit is the picture element, or the pixel. Okay? So we can decide to carry out analysis at that picture element, so that for each pixel, we want to understand about the object in that pixel. This is the traditional method of carrying out remote sensing analysis. However, the disadvantage of this is that you lose contextual information. For example, if there was a single pixel that was water, you lose the information on what is neighboring this water. So there's a second method of carrying out image analysis, and it's called object-based image analysis. And here, we try to define objects first and then carry out analysis at that object level. So the unit of analysis is an object which is derived from a collection of neighboring pixels, a collection of neighboring cells. Because you are using the neighboring cells, so you have the advantage of having contextual information. So for example, you don't just look at a pixel. You do not expect, for example, to have a high-rise building in water. So if you are to get an object that looks like water inside, an object that looks like a building inside water, you will question the context. Is this really true? So the object gives us that advantage. In terms of image processing methods, we want to talk about image segmentation. We have an image initially, which is just a picture. Yet objects are distinct, are distinct entities. So we want to move from this picture to distinct entities. So the first thing to move to these distinct entities is segmentation, which is the process of partitioning an image into meaningful objects. Segmentation simplifies the image or the picture into objects with reasonable contextual information. Okay? Each of the pixels in a segment have a similarity characteristic. So that is one thing that we always need to understand, that before we segment, there has to be a similarity criterion. Neighboring objects should be significantly similar to each other, in the sense that if I have one object and there's a neighboring object, the reason why that object is not part of this object is because the two are dissimilar. Okay? There are various methods for segmentation. One of them is threshold. You know, when you have an image, you can plot a histogram of each of the pixels. So for example, if I have an image of elevation, I can plot a histogram of the elevations. So a thresholding method uses the peak of the histogram to separate two objects. Then an edge-based method, it uses discontinuity, in the sense that if I had one object, at the point where it is discontinuing from the next, that is where I segment it. Yeah? Then there's clustering method. In a clustering method, I have a clustering criteria so that pixels are clustered. Okay? Then the other method is a partial differential equation method. A partial differential equation method, it means you find an equation that can help you in segmenting your object. And artificial neural networks. In artificial neural networks, normally there is a learning. You provide a few training sites, and then and you provide an algorithm so that your image can learn. Okay. So again, here we've provided the reference that you can go to and understand about segmentation. In terms of image classification, this is very important. There is no way you'll attend any remote sensing lesson or training or without talking about classification. But then what is classification? It means we have our objects and their objects are similar. So we put them in different classes or in different categories. For example, if I had an image of the city, there are buildings and there are roads. So I can decide that buildings are in one class called buildings, and roads are in another class called roads, and green spaces are in another class called green spaces. So the particular steps for image classification are: one, you have to consider that we have an objective. We have an objective for carrying out this classification. So we have to select remote sensing data, meaning I have to select data that will allow me to pick these classes. Because of the spatial and spectral resolution of images, this is a very critical step, because if you choose images that are of low resolution, then you cannot select classes at high resolution. Then you determine a suitable classification system. So for example, are you going to use a method that has been developed by FAO? Are you going to use a hierarchical method? Yeah. And then number three, you select the training samples, because the computer by itself is not intelligent to do everything by itself. So training sample, it means as a human being, I know where a few buildings are. Can I tell my computer, can I tell my algorithm what buildings look like? And they can look from the image and pick these buildings. Then image pre-processing. Image pre-processing is sometimes our images are not in the same location, or sometimes there are errors that may have occurred when the image was being collected. So we try to correct these before we carry out an analysis. Then we go to feature extraction. Here I want to explain it from a point where a single image, a single remote sensing image can have many different layers based on how the electromagnetic spectrum is subdivided. So it can have many different layers. Assuming I have one image that has a red band, a green band, and a blue band. Okay? If I have these, then I have to decide which of these bands will clearly give me vegetation. And sometimes I have to combine the bands and create other indices so that I'm able to accurately extract the features that I'm interested in. So this process of selecting bands or adding additional indices is what is called feature extraction. Then selection of suitable classification approaches. There are various classification approaches. We'll talk about them in the next slide. One can be supervised, another can be unsupervised. Supervised just means that I train my algorithm, I train the computer to carry out, I supervise it. And unsupervised is where I allow the computer or my tools to automatically carry out a classification. Okay? Then once we carried out a classification, we have to carry out a post-classification processing. Because, for example, there may be a single pixel that is misclassified. So I have to clean that. And then I carry out accuracy assessment. We will explain this again. My intention is not to go through every aspect of this slide. My intention is just to show that there is a criteria for how you choose a particular classification method. Okay? So for example, if you have training data, then you can use a supervised classification. If you do not have, then you use an unsupervised classification. Again, we'll provide you with a slide so that you can go through these and the slide and the references so that you can go through each of them and understand why you choose a particular classification method. The list goes on. So, for example, if your image is so detailed that you can see objects, okay, and you have the tools for picking out those objects, then you can carry out an object-oriented you can use an object-oriented classifier. Another type of analysis are called spectral indices-based analysis, in the sense that from the original image, I have various bands, and sometimes I can combine a few bands to give me an index that has more information. Some of us may have heard about vegetation indices. For example, there's a vegetation index called Normalized Difference Vegetation Index. It combines the near-infrared and the red bands to give us an index with more information, so that instead of using both the bands, we can just use a single index. There are many of these. There are many of these for different purposes. So when we just talk about vegetation indices, there's one where you want to adjust for the effect of soil, when you want to adjust for the effects of the bare soil. So there are various kinds of indices, and these are also very useful, and they're used for various applications. And we'll talk about applications at the end of the slides. I don't want to go into the particular examples of the applications. Then accuracy assessment. So you carried out your analysis. You need to check whether the results of your analysis are in agreement with the reality, are in agreement with what is on the ground. Accuracy assessment is important because of the following reasons. One, we want to improve our method of analysis. Or number two, we want to quantitatively compare methods. So for example, we use an object-based method and a pixel-based method. We want to compare the two. Or number three is to provide the basis for using results of a remote sensing image. So for example, when I say that all the urban areas were classified at 90% accuracy, then people can rely on that information. There are various methods for carrying out accuracy assessment. One is a visual inspection. If I was mapping water bodies, and I can look at my map and see that this is indeed not a water body, so that is a visual inspection. Okay? Then there's another method called non-site specific analysis. It means I've carried out my analysis, but I try to check whether the results that I'm getting will apply in another site. Okay? Then there's another method called difference image creation. So I have two images, one that is a reference image and another one that is the one that I've classified. And I try to do the difference, to just do a subtraction of the two to see whether there is any difference between them. Then there's a method called error budgeting. Error budgeting is where we look at each process of our analysis. This is the process of capturing data, the process of analysis, and every process that the image has gone through, and try and look at what are the potential areas that may have come at each of the processes. And then ultimately, there's a quantitative accuracy assessment, where we try to put a quantity on the quality of the results that we've got. And this is an example. So I've carried out an image analysis and I've come up with 4 classes, A, B, C, and D. Okay? Then I pick samples, assuming I pick 400 samples from this data, 444 samples from this data. So I have a reference data which is accurate, which I trust. I pick 400 samples from that. And in those locations, I also pick data from the data that I've classified and try to compare from the data from my reference and from the data from my classified data. How do they relate to each other? Quantitatively, can I say something about the accuracy? So when you have this kind of analysis where you are comparing one data against the other, it is called a confusion matrix. And there are various aspects of errors of accuracy that you can look at. One is the error of omission or an error of commission. So basically, error of omission you try to look at what percentage of this data has been wrongly excluded, or what percentage has been included in another category that they should not belong to. Then there's overall accuracy. The overall accuracy, it just indicates the overall quality of your classification. So here basically is what is it in my reference email that has been accurately classified. Then there's a producer's accuracy. The producer's accuracy, it indicates the quality of classification of a training pixel. So for example, if from my training data, from the data that I know, from what I know this is a building, I know this is water. What percentage of what I know has been accurately classified? And then the user's accuracy, it indicates the probability that a prediction, basically my classification, the results that I've got from my classification, how accurate is it in predicting my reference? When I compare it to the reference, how accurate is it? So these are some of the parameters that we can use to check whether our data is accurately classified. So of all the methods that we talked about, a mixed method approach is better. So for example, you don't just take one image, you don't just take one type of image and make a conclusion on it. If you can combine images, if you can combine data, if you can combine the processing methods, then you get better results. So the whole point is, it's not just one, there's no one method that fits all. The more you combine these methods, the better the results that you get. Some of the tools, because we talked about remote sensing tools and methods, and in particular in this case we are interested in open tools that you can freely get and freely use. There's Quantum.js, there's R. R is good because it provides a platform for analysis, but you can also combine it with other libraries. Same applies to Python. So it provides a platform for analysis for your coding, but you can get additional libraries and you can get additional tools that other people have developed. Then there's eLuis, which is a desktop software that you can use for remote sensing. Then the next one is called Orfeo Toolbox. And this is important, particularly when you want to carry out object-based image analysis and you want to combine it with, for example, Quantum.js. So you can add it as a plugin in Quantum.js and carry out object-based image analysis. Then there's Google App Engine. I talked about it briefly, but this provides a basis for carrying out analysis. So you write small codes that can access data, can analyze the data and present this data. So it both provides the data, the tools of interacting with this data, and how to visualize your results. And there's Grass and there's Saga. And obviously this list is not conclusive, but the intention of this is just to show you that they are open tools, they are open and free tools that you can use to learn about remote sensing. In terms of the applications, so why should anybody be interested in remote sensing? Particularly when you talk about remote sensing and natural resources. One of the areas of application is water resource mapping. For example, mapping surface water characteristics. Mapping surface water characteristics. That is one of the areas of application where remote sensing is being used. Another example is when you want to understand about land health and land degradation. So from remote sensing data, we can get various parameters that tell us about land health, that tell us about soil characteristics. So if you are interested in understanding land health, soil fertility, you're interested in understanding how the land can be productive or how the land is being degraded, then remote sensing is one of the tools that you can use. The advantage of this is that it provides you the ability to understand a large area. For example, if you want to understand the whole of Africa, it's not possible to do something where we go to every farm in Africa, but you can get remote sensing data that provides us with a clear picture. And for each of these slides, again, we provide the references where you can go into the details. Then forest mapping, or when we want to understand about forest fires or forest degradation. And in this particular work, it's a work that we are currently carrying out to understand the changes in urban forests in the city of Nairobi. So again, from remote sensing, we can be able to pick tree cover characteristics, and from these tree cover characteristics, we understand the changes both in the geography and in time, and what is driving forest cover change. Then there are invasive species. There are trees that are growing in the dryland areas that are affecting the ecosystem in the dryland areas. And it is very important to understand the characteristic of these trees, the drivers, what causes these trees to continue expanding in these drylands, and how can they be removed, or how can we make better use of them. So remote sensing has also been used in mapping invasive species. Then crop modeling and food security. Food is one thing that we all can relate to. And sometimes we want to understand what crop is suitable for each place. We cannot move to each place to test their crops. We can use remote sensing that tells us the phenological characteristics of different crops, the land characteristics, the topographic characteristics, and then use it for crop modeling. Then wetland and coastal mapping. In this example, we mapped seagrass and coral reefs under the water. And we use remote sensing. Particularly, we use Landsat imagery, and there's something called band ratioing. So sometimes you can have two bands, and when you carry out an operation on them, for example, you divide two different layers from remote sensing, it tells you something that is beneath the surface, something that you will not see if you just look at a single band. So this is an example that we applied in Mozambique to map seagrass and coral reefs. Then land use and land cover mapping. Understanding what is where on land, what class is where on land, and how is it being used. This is a very common analysis method, and it is one thing that most of us will go into remote sensing will have to do it. And apart from those applications, let's briefly talk about drones. Okay? Lately, we've heard about drones, and we've seen drones being used to capture videos. We've seen drones being used for different purposes. How can these be used as remote sensing tools, particularly for natural resources? Drones, they are unmanned aerial vehicles. They can have sensors with them, they can have cameras with them, and those cameras can have various characteristics. And those sensors then become very essential for capturing data. Because they can fly closer to the surface, means they can capture information at very high resolution. And when they capture information at very high resolution, then this gives us information that we can use for very detailed analysis. For example, if you are a surveyor and you need to map to survey a road from one city to the next. Traditionally, surveyors will just walk on a daily basis, covering distance from one place to the next. But now with drones, you can get very high resolution data. And when I talk about very high resolution, less than a centimeter accuracy, and use this for your surveying. Use this to create digital elevation model, orthomosaic images, and use this for your analysis. If you are into farming and you want to do precision farming, so you want to understand what is the vegetation index, what is the vegetation characteristics of your farm. Again, you can use drones and carry out estimate, for example, the NDVIs, the vegetation indices, and have this to help you in your precision agriculture. So the demonstration that we are going to have is going to be on the drones, and it's just a demonstration so that people can be able to appreciate the data. there's sample data. There's a company called Wingtrend. I talked to them and they say you can use their data for free. They have sample data that you can use for your analysis for free. And when I finish the slides, then I'm going to go into it. So in brief, we've covered so much ground. We started by defining what remote sensing is. We talked about different concepts of remote sensing. We talked about different tools. We talked about different methods. We talked about different applications. And we talked about how it can be used in different areas of application. Our aim was to give a motivation on why remote sensing can be used, and particularly how it can be used in natural resource management. I hope this presentation has given you an idea on what remote sensing is, and we designed it like this because of the nature of our audience. We didn't want to go very high level, because then it means that some of our participants will not be able to follow what we are talking about. Should there be any need for us to have an additional training in this particular field, then we are still glad you can communicate to us, and we organize targeted training to go into the details and to go into the particular applications of remote sensing. At this particular time, before we go into the questions, I'll just get off the slides and show us, give a demonstration. It's a 3-minute demonstration with the LiDAR data. Thank you. With the drone data. Thank you.
Clearly, you can put some questions in the chat section.
Yeah, I'm informed that there are questions that are already in chat. And let me just do this demonstration.